Hello, my name is Emma Graham, and today I'm going to be talking about my project, the inhibition of pulmonary surfactant function through exposure to e-cigarette vapor. So just to start, what even is vaping? Well, it's the use of an electronic cigarette, which utilizes an e-liquid, which gets heated and vaporized to produce an inhalable vapor. And although originally regarded as a smoking cessation tool, we have to wonder, is that really still the case? Nowadays, it's hard to deny that one of the main targets for marketing of e-cigarettes and vaping is actually, kids and young adults, these previous non-smokers who get into vaping recreationally. And so what is in this e-liquid that people are vaping? Well, the main components of the e-liquid are propylene glycol and vegetable glycerin, which are both regarded as safe food additives. And now, customizably, you can have further additives, which include artificial flavoring, which give us these, nice, appealing flavors, as well as varying nicotine content, and a wide variety of devices are also available on the market, ranging from the simplest and disposable up to very complex and customizable mods. So vaping as a habit itself is very diverse and very customizable to the user. And now, why do we care and why is vaping bad? Well, we've seen e-cigarette or vaping-associated lung injury, also known as EVALI. We've seen an outbreak of this in North America, as well as continued reports of this, particularly amongst this youth and young adult population, where vaping continues to increase. So even though we have millions of young people vaping across the world, some of them will get EVALI and some of them won't. And we have to ask ourselves why. Well, to answer this, first we need a better understanding of the mechanisms leading to the lung injury. And so our take on this is to look at vapor inhalation in the lungs and how this affects pulmonary surfactant in the alveoli. Because during a deep inhalation of vapor, the vapor will reach the alveolar area and it will interact with pulmonary surfactant. So what is surfactant? Well, it is a complex mixture of lipids and proteins which lines that alveolar surface, and its job is to reduce surface tension in the lungs to near zero values during exhalation. So a quick demonstration of this, if this is an alveoli here, we can see high surface tension, and then as the area of the alveoli decreases during exhalation, surface tension remains high, and this leads to a very unstable alveoli and will result in alveolar collapse, and you will not be able to breathe. However, with the addition of surfactant, we see reduced surface tensions, and then as the area of the alveoli decreases during exhalation, surfactant is actually able to reduce surface tension values to near zero. And this is what prevents alveolar collapse and maintains lung compliance. And so we do see surfactant dysfunction in cases of lung injury, for example, in neonatal respiratory distress syndrome, where newborns who are born premature don't have enough surfactant and will not survive without it. They can't breathe. So they are treated with the addition of an exogenous surfactant. So overall, it's just important to remember that low minimum surface tension is absolutely essential for lung function. So now our hypothesis is that exposure to e-cigarette vapor will actually disrupt surfactant's ability to reduce alveolar surface tension and thereby contribute to lung injury. So our objective for this experiment was to test the effects of vapor exposure on surfactant function in vitro. And how we did this was to first start by mimicking vaping. So we used BLESS as our model surfactant, which is bovine lipid extract surfactant, and we placed this in a syringe attached to an e-cigarette. We were then able to draw the vapor right into the syringe to directly expose it to the surfactant, leave it for 30 seconds, expel, and then we repeated this 30 times to mimic 30 breaths. After exposure, we analyzed the samples on our surfactometer. And so briefly, how this machine works is we put a drop of surfactant on a pedestal in an environmentally controlled chamber, which is hooked up to a motorized syringe and a computer. And through controls on the computer, we're actually able to compress and expand the drop to mimic the compression and expansion that occurs during breathing in the lungs. And we have a camera set up that takes very rapid pictures of these dynamic changes and is actually able, through the computer software, able to analyze the surface tension of the drops. And so we're able to get minimum surface tension values for each of these compression cycles. And now we have 3 experimental variables we wanted to test in this exposure phase. First, looking at the e-liquid vehicle itself and seeing if that on its own was able to inhibit surfactant. Next, looking at 3 different common style devices. And lastly, examining different flavors and nicotine additives to see if they had any further effects. So for our first experiment, looking at just the e-liquid vehicle itself, we saw that minimum surface tensions increased after exposure to even just this e-liquid vehicle with no further additives. So over here on our y-axis, we have minimum surface tension plotted against our compression and expansion cycles that the sample underwent on the surfactometer. In the white circles, we can see our air control, which was blessed, that was just exposed to air, no vapor. And in the black squares here, we have our vapor exposed bless. And we can see increases in the minimum surface tensions across all cycles. Next, we wanted to compare these effects across 3 different devices ranging in power and style. And again, we can see here in our white circles, our air control is significantly lower than our vapor exposed samples. And we can see that minimum surface tensions increased independent of the device used. All 3 were able to inhibit surfactant. Lastly, we wanted to look at different flavors. So we had a variety of flavors from fruity to drinks to tobacco, some with and without the addition of nicotine. And these are plotted at the 5th compression cycle. And what we saw was that for most of these flavors, the flavored e-liquid inhibited surfactant to a similar extent as the unflavored, just normal vehicle. However, in 2 cases, red wedding and menthol, we actually saw further increases in this minimum surface tension compared to the vehicle. So we wanted to look at these flavors a little bit more in depth. And so if we look at the plots for these flavors across all 20 compression cycles, we can see here, this one on the left is for menthol. So we have our air control, and then we see higher minimum surface tensions with our vehicle, and then even higher surface tensions across all 20 cycles with the menthol exposed surfactant. Interestingly, when we looked at the red wedding, we can see that again, we start with significantly higher minimum surface tensions. However, this decreases cycle by cycle until about the 10th compression cycle, where the red wedding flavor actually lines up comparably with the vehicle control. So although we saw further inhibition by both menthol and red wedding, we saw different responses between the 2. So just to sum up, the e-liquid vehicle itself was able to inhibit surfactant, and this effect was seen across all 3 devices we tested. And some flavors, particularly in this case menthol and red wedding, are able to further inhibit surfactant. So overall, vapor exposure leads to impairment of the pulmonary surfactant system through increases in minimum surface tension. And although these increases in minimum surface tension alone may not be the sole cause of vaping-associated lung injury, we conclude that inhibition of surfactant function can contribute to lung dysfunction and be an important factor in this lung injury. And it may also lead to increased susceptibility to further injury. Thank you.